Continuing with our section 4.1 lecture, the first thing we need to introduce after going over partition numbers and finding where a function is increasing and decreasing is the definition for a critical number. So we say a critical number is a partition number that is in the domain of the original function. So that means when you find your list of all possible partition numbers, you then check each of those partition numbers to see if you can plug it into the original function and get an actual answer. If you end up getting does not exist, an imaginary number, or undefined, then that partition number is not a critical number. But if you get something like f of 2 equals 5, meaning you got a real result by plugging in 2 into your function, then that x equals 2 value, that partition number, is a critical number. So let's go over an example with this. I've already pre-created this one. We have some function f of x equals 1 over x minus 2, and we want to decide whether or not we have any critical numbers, and if so, what are they? So the first thing that we would have to do here is to find the derivative. So just really quickly, I've already done that. You could use the quotient rule or bring up this x minus 2 into the numerator and apply the general power rule. In either case, just quickly solving this, we would get f prime of x is negative 1 over x minus 2 squared. To find the partition numbers, remember we set the top and the bottom equal to 0 of our derivative. In this case, the top cannot be set equal to 0 because there are no x's. Negative 1 can never equal 0. So we just set this x minus 2 quantity squared equal to 0. And in fact, this squared doesn't even matter. That's just saying we have x minus 2 being set equal to 0 2 times. At the end of the day, that just means we're setting x minus 2 equal to 0 and solving. If that seemed confusing, just remember you could always take the square root of each side, which would leave you with x minus 2 equals plus or minus 0, which is still x minus 2 equals 0. So whenever you have some factor with an exponent equal to 0, you can always ignore that exponent. Now we'll go ahead and solve for x to find the partition number's value. So we'll add 2 to each side. And when we do that, we get x equals positive 2. That is our partition number. Now, to decide whether or not this is a critical number, we are going to take this x equals 2 value and plug it into the original function. We're going to find f of 2. And when we find f of 2, we're plugging 2 in for x. That gives us 1 over 2 minus 2. Simplifying, we get 1 over 0. And anything divided by 0 is undefined. So what does that tell us? The only option that we had for a partition number, x equals 2, is not a critical number because it doesn't exist in the domain of the original function. When you plug it back into the original function, you get division by 0. So the function f of x equals 1 over x minus 2 has no critical numbers. With that, we're going to try another example. So this is continuing on with section 4.1. And for this example, we have f of x equals x squared minus 1. And we want to find the critical numbers, and we also want to find where it is increasing and decreasing. So a continuation of what we did on our last video, part 1. So to start off, remember to find partition numbers. You first find the derivative, f prime of x in this case. The derivative of x squared is 2x. The derivative of negative 1 is just 0, so it goes away. So to find the partition numbers from here, we're going to take our derivative and we're going to set the top and bottom of it equal to 0. Remember, if it's just something like 2x, some polynomial, we put that over 1. So when you set the top and bottom equal to 0, you just end up getting 2x equals 0. And since 1 cannot equal 0, we don't even have to worry about the denominator. So solving for x, we divide each side by 2, which gives us x equals 0. That is our partition number. So we take this partition number, and now we have to check it in the original function to see if we get a value that exists, something that is defined. And if it is, it will be a critical number. If it isn't, then it is not a critical number. It is only a partition number. So we will find f of 0, which plugging 0 in for x in our original function gives us 0 squared minus 1. So f of 0 equals negative 1. Negative 1 is a real result, which means x equals 0 is a critical number. From here, we now have to find where it is increasing and decreasing. So that goes back to the table or number line method we were working on in the last video. So in this case, I'm going to use the table method. We are checking x, our partition or critical number, in the derivative. And remember, the way this works is we take our partition number and we check a value to the left and to the right of it. So we're going to check negative 1 and positive 1 since they are to the left and right of x equals 0. So when we plug in negative 1 into the derivative, we get 2 times negative 1 just gives us negative 2. All we care about is that it is negative. Because it is negative, that tells us that everything to the left of x equals 0 will be decreasing because the derivative is negative. So we can make a note there, decreasing. When we plug in 0 into our derivative, well, we already said that's our partition number or critical number, and that occurred when we set the derivative equal to 0, so the result will just be 0. And when we plug in 1 into our derivative, we get 2 times 1 just gives us 2. 2 is a positive number, so the first derivative is positive. With everything we plug in to the right of 0, that means it is always increasing. So now we can create our intervals to decide where the function is increasing and decreasing. So we'll start with decreasing. We'll say the function f is decreasing on the interval, let me line this up, it's decreasing on the interval that contains all numbers to the left of 0, which means if we go all the way to the left, the lowest number we can think of, that would be negative infinity. And if we continue all the way until we reach 0, when our first derivative is no longer negative, we'd go from negative infinity to 0. And remember, we always put a parenthesis because you can never say that it's increasing or decreasing at one exact value. And now we also say f is increasing on the interval, and in this case we want to pick every number to the right of x equals 0 because we said that's when the derivative will be positive. That means the function is increasing. So in this case, we start at 0, not including it, so we put a parenthesis, and we continue all the way to positive infinity because every number to the right of 0 tells us f is increasing. So we have just found the critical number, x equals 0, and we've also found where the function is decreasing on the interval negative infinity to 0, and where it is increasing on the interval 0 to infinity. Which makes sense when you think about what the graph of x squared minus 1 looks like. That's a parabola that would look something like this, just to give a quick sketch. So if you look at all the values starting from negative infinity to 0, they are constantly decreasing. The y value is always decreasing until it reaches the vertex, and then at that point, from 0 to positive infinity, the y values are always increasing, which is exactly what we said for our intervals here. Okay, so for the last problem, just like in the previous video, I suggest that you try this one before watching me go through it. In this case, we have f of x equals 8 times the natural log of x minus x squared. And with this, we want to find the critical numbers. So to find the critical numbers, just a moment, actually, I'm going to give you just a moment to pause the video to try this out on your own. Okay, now to find the critical numbers, remember we first start by finding the partition numbers. So we'll find f prime of x. The derivative of 8 natural log x, remember the derivative of natural log x is 1 over x, so 8 times that would be 8 over x, minus the derivative of x squared is 2x. Now, before we continue finding our partition numbers, we have to turn this into one complete fraction. If we try to find them using this, it would be a little bit more complicated than just setting the top and bottom of the fraction equal to 0. So we are going to put this 2x over 1 and find a least common denominator between x and 1, which is just x. So we multiply the top and bottom of the right fraction by x, which gives us 8 over x minus 2x times x is 2x squared, over 1 times x is x, which leaves us with 8 minus 2x squared all over x. And finally, from here, we are going to factor this completely. When we set the top and bottom equal to 0, if it's completely factored, then we can set each factor equal to 0 and quickly solve. So, the first thing we can do is factor out the common term of 2 between this 8 and 2. So when we factor out a 2 from the top, or the numerator, we're left with 8 divided by 2 is 4, minus 2x squared divided by 2 is x squared, all over x. And when we factor 4 minus x squared, this is a difference of squares. We have 2 perfect squares being subtracted. So remember, whenever you factor a difference of squares, you take the square root of the first term, which is 2 in this case, plus the square root of the second term, which is x, and then again the square root of the first term, which is 2, minus the square root of the second term, which is x, and put that all over x. And now that we have this, we can set the top and bottom equal to 0, which will give us our partition numbers, and then check those in the original function to decide whether or not they are critical numbers. So, we set the top equal to 0, and because it's already factored for us, we can just set each factor equal to 0. So 2 plus x equals 0, 2 minus x equals 0, and now we set the denominator equal to 0, and this gives us all of our possible partition numbers. We'll subtract 2 from each side in the first case, which gives us x equals negative 2. We'll add x to each side in the second case, which gives us x equals positive 2. And in the third case, x equals 0 is already done for us. So we have partition numbers of 0, negative 2, and positive 2. Let's check in the original function though. Notice in the original function we have 8 natural log x minus x squared, and this is where it's handy to remember what graphs look like of these general parent functions. So remember, a parent function is just the base function before you do anything to it. So thinking about natural log of x, remember that the graph of natural log of x, I'll go ahead and put it over here, looks something like that. Notice that we cannot plug any x value that is less than or equal to 0 into this because there is no graph that results from it, meaning the domain is 0 to infinity. So going back to this step here, these 3 partition numbers we found, we can immediately eliminate x equals negative 2 and x equals 0 because neither of those can be plugged into the natural log of x. It will give us an undefined or does not exist, so they are not critical numbers. The only option is x equals 2, so if we find f of 2, we get 8 natural log of 2 minus 2 squared when we plug that in for our x's. And with that, it doesn't matter what this result is. All that matters is This has a result. If you were to plug this into your calculator, you would get a real answer out of it, which means x equals 2 is a critical number. It is always very important to remember in your initial problem to check your domain, because that is the only way that you will know if you're working with a partition number or a critical number.